Everyone here at DARPA knows that our mission is to make the pivotal early investments in breakthrough technologies for national security. And what I want to do here at my last all hands is to show you the full sweep of the work that we're doing at DARPA and the impact that it's all about. Now, this is what Steve and I get to do all the time. We look across that portfolio and we think about it and we try to make sure it's balanced and driving to the highest impact we can achieve. And we in the Tech Council always get to look across that whole portfolio, but I wanted to make sure that I shared it with everyone here because this portfolio and the successes that come out of our work at DARPA belong to every single person in this agency. Whether you're a government employee or a CETA contractor, whether you're part of the technical team or part of the support team, we need every single one of you to do this work. And so when DARPA succeeds, everyone in this agency owns that. And the second reason that I wanted to share all of this with you is I personally could not possibly be prouder of the work that we're doing together. So I wanted to celebrate that with you. Okay, so across what I'm going to talk about today, you will hear three broad themes that frame the work that we're doing at DARPA today. The first one is about completely rethinking complex military systems. And the reason for that is that we live today in a time when the big monolithic systems that have been so powerful in our military capabilities until this point, we're now at a point of diminishing returns for these big systems. Think about fighters and huge satellites and big RF arrays. In every one of those cases, we're at a point now where it costs more and more and takes longer and longer to achieve just incremental advances. And so at DARPA today, we are inventing new military systems, but also new military systems architectures. And our objective here is to be able to move at the pace of the underlying technology and to move at a pace that far exceeds where the adversary can go. And I'll tell you several things that we're doing that fit into that general theme. You'll hear that across many of the stories I want to share today. The second major thing that you'll hear is about the information revolution. We're halfway through, maybe 40 years into something that's maybe 40 or 50 years into a century-long explosion in information capabilities. And today we're in a time when it's critically important to be able to trust the information and the information systems that we're so reliant on, and then to start harnessing that data and creating deep value out of it. And I'll tell you some stories about that as well. And then finally, this last curve represents something that we have always done at DARPA throughout our history, and that is to scour the research horizon to look for the places where people are running to conferences and arguing and papers are flying. When you see that kind of excitement in new research fields, those are the places where the seeds of the new technological surprises are going to come from. And so actively finding those areas and driving into them and starting to build technology out of basic research. That's a third theme that you'll hear in several of the stories that I want to tell you. Okay, so DARPA is huge, right? We are about a quarter of the Department's science and technology investments, about almost $3 billion. At any moment in time at DARPA, we have about 200 active programs. So what I'm going to show you across that huge portfolio is about a dozen big ambitions that we have, huge impact that we're aiming to achieve through collections of our programs. And with each of those, I'll give you some examples of specific programs. It's been really hard to choose because there's so much good work going on in the agency. But let me start with this first big ambition, which is to protect against weapons of mass terror. We're living in a time in which technologies from nuclear technology to new chemical weapons technologies to biological threats, all of these technologies are becoming easier to get access to, and they're becoming cheaper. And that means that over time, terrorists have access to increasingly powerful technologies. And several of the things that we're doing at DARPA, programs across 3 different offices in this case, are focused on this issue of how do we protect against against this advance in weapons of mass terror. And I'm just going to tell you a couple of stories from this area. The first one is a program called SIGMA in DSO. Today, we really don't have an ability to continuously monitor for nuclear and radiological threats, for example, across the city. And the reason for that is that to do that, you have to look for really small signals against a noisy background of radiation in our built environment or people who just had radiological medical treatments. And all of those false alarms essentially make it impossible to keep track on a continuous basis of the small shifts that could tell us that something is amiss. The SIGMA program set out to radically change that. It's made enormous progress in just a few years. The first thing it did was to develop a device, this is one of them, that took the very complex, huge, costly sensor systems that we have and collapsed it down into a device that's easy to carry that only costs $400. We've bought 10,000 of those, and now we're starting to build them into networks that can be carried around a city and that can not just give you dosimeter information, but actually give you the spectrum to show what kind of signature we're getting, compare the signatures we might get against threat profiles, and when we see something that emerges out of that background that could be a threat, we're now in a position to give an intelligent alert to first responders with very low false alarm rates. Huge technical progress, but one of the things I'm really proud of with this program is that we're starting to do trials now in big cities in Washington and New York, and very soon I think we're going to be in a place where we have operational capability that allows us to be able to find nuclear and radiological threats before a terrorist can detonate a bomb. And this is a great example of something very direct that DARPA is doing that's keeping millions of people in America safer. So that's a story that's well on its way, and we've made, I think we can see the impact palpably in front of us. Let me tell you a different area where I think we're in the middle of a longer journey, and this is about a kind of a mass terror threat that today we face from Mother Nature. It's the threat of infectious disease. This is a curve showing new cases in the U.S. from H1N1 a few years ago. More recently, of course, we've been reading about Zika, before that about Ebola. This is a continuing series of threats that comes at us. And this is before terrorists have biological tools that allow them to get in the game. So it seems like a good idea to figure out how we're going to get ahead of these problems. Now, here's the issue. Today, when we have this kind of an infectious outbreak, in the case of H1N1, we ran as hard and fast as we knew how to go. And by the time we identified the actual virus that was the problem, figured out how to build a vaccine, started vaccine production to grow these enormous biomolecules, got that vaccine approved, got it into human beings, waited the weeks that it takes to develop immunity. By the time all of that happened, the first individuals who were protected, that happened on the right side of this curve. In other words, the disease was starting to burn itself out naturally by that time. In a retrospective analysis estimated that fewer than 2% of potential cases were averted from that vaccine. Now, H1N1 caused a number of problems, but it was not nearly as deadly as the 1918 influenza pandemic, and you can only imagine if these were not just cases of infection, but deaths, what kind of panic we would have had in this country. So this is completely unacceptable. DARPA had a huge ambition starting a few years ago with the ADEPT program and others in BTO. And the question we were asking was, what would it take to prevent the next pandemic, to nip infectious disease in the bud before that extremely huge outbreak happened? And we started down the path to do two things. One was to figure out how to not just treat people with a vaccine, an antigen that triggers their own immune system, but also to find ways to scale antibodies from survivors of infectious disease. This is something we know how to do sort of on a one-to-one basis today, but we didn't have ways to scale it before. The second thing that we did was set out to find ways to collapse the amount of time that it takes to build these huge biomolecules, whether it's the antigen for the vaccine or the antibody that's been identified from survivors. In either case, there's this very lengthy process of growing these big biomolecules in cells, in eggs, for example. And we knew that that simply wasn't going to cut it. So the other branch of what we worked on was a method to use genes to encode those big biomolecules and develop techniques to deliver those gene codes directly to the individual's body, where our own cells could boot up that software instruction encoded in that gene and use ourselves as the bioreactor to create those big biomolecules that we need. Now, when you do that, it radically shrinks the amount of time it takes to produce the therapy, because now it's this much simpler molecule that you're building, this DNA fragment or an RNA fragment. And when you've built that medication, you now don't have to ship it in an environmentally controlled way. It's something that's shelf stable. It's a very, very different process. And as a consequence, we are beginning to see the technologies come together that could, in fact, allow for people to be protected very, very quickly within a few months of the time that a new infectious disease strain is identified. Now, this picture is still an ambition. The early work that's happened today has shown we've gotten through phase 1 clinical trials for gene-encoded antigens for vaccine treatments for diseases like chikungunya and Zika, and so we're off to a good start and still a lot more work out ahead here. So that's protecting against weapons of mass terror. Let's talk about another huge ambition, and this one is very, very vast. It's about the air and maritime combat capabilities that we're going to need to deter and defeat a sophisticated adversary. Now, in the 70s and 80s, DARPA worked on the technologies, precision strike and stealth, the systems of that era that have in fact formed the backbone of our conventional deterrent and that have in fact shaped adversary behavior for many, many decades today. Now, after a mere 40 years, guess what? The adversary gets a move, and adversaries around the world today are developing the techniques and the tools that will render those very powerful second offset technologies increasingly obsolete. And so today it is an important time for radical new thinking about the kinds of combat capabilities that would deter a sophisticated adversary. And the only way to deter a sophisticated adversary is to show them that they just don't even want to start, because they will lose so decisively that it's not even worth taking that journey. So a huge number of programs, couple of dozen programs, some very significant activities in multiple offices across the agency going after this incredibly huge objective. And I want to talk about a few threads through this work, and I will start with weapons. In 2008, DARPA started the Long-Range Anti-Ship Missile, LRASM program, and this particular program started out of a very clearly identified need that PACOM had been very aware of. They said, we are outsticked in the Pacific. If we don't get missiles with longer range, we are simply not going to be in a sustainable position. DARPA jumped on this in 2008 and started a program that today has resulted in a program in the Navy that's on track for early operational capability in 2018, an amazingly short time to get a new weapon system fielded and operational. Two things happened to get us from start to this point, and the first was this kind of very successful flight test. This is the next picture is what it looks like when you're on the receiving end. And with a couple of these kinds of early flight tests, the LRASM program was able to convince the Navy that this approach really could work. And the Navy programmed money to take LRASM forward into an operational capability. And then DARPA did the second important thing in this program, and that was to say, well, if we just let go of it, it's going to proceed at the conventional pace of acquisition. And we thought there was a huge opportunity here to team up with the Navy and to keep LRASM moving at the DARPA pace. And that's exactly what we did. We stood up a LRASM deployment office, and we ran that next leg of the race side by side with our partners in the Navy, handed off to them, and now they're taking it across the finish line and turning into something that will serve our warfighters in theater. That's something that happened a couple of years ago. What's happened in our weapons story, there are many more chapters at DARPA. We're in the process of turning hypersonics technology from just the development of core technologies to prototype weapon systems in Hawk and TBG, and that's going to be an enormous advance in U.S. military capability. But When we talk to our colleagues in uniform, this is what they tell us they really want. Laser weapons that attack at the speed of light. And this is what they tell us they want. We know in their heart of hearts this is what they really want. And as wonderful as those ambitions have been, tragically, this is what the warfighter has gotten so far. Yeah, that's a laser. It's the size of a 747, and you know that's just how hard it was to actually deliver enough power on target to have a laser weapon. Well, DARPA is finally beginning to radically change that, and we're doing it by driving fiber laser array technology. These are laser technologies. This is a laser technology with far greater efficiency, far greater scalability, with the ability now in these systems to adapt to environmental conditions, all of which taken together means that in a very compact form factor now we can start delivering enormous power on target. Today we are about to embark on field tests for a system that is small enough to fit on a large helicopter. We're developing the core technology so that ultimately we'll be able to get powerful laser weapons, compact enough to deploy on something the size of a golf cart. A huge advance in this area, and finally taking something from comic book to reality. So that's weapons. There's a huge amount of activity going on in both air and maritime as we're working on these next generation combat capabilities. Let me take you on a thread through the maritime story because I think you'll see how some of the pieces come together. This, of course, is Sea Hunter. This is our self-driving ship developed in the ACTIV program in TTO. A number of years ago, we set out and said, gee, what if you had a ship that could leave the pier, navigate by itself across the open oceans without a single sailor on board, simply controlled with sparse supervisory control, not remotely piloted, but sparse supervisory control. Wouldn't that open up amazing options for the Navy? Now, in this case, unlike LRASM, in this case, when we started, the Navy said, "Are you kidding?" And then they even tried to stop us. We sort of laughed at them. And then it's been marvelous to watch the Navy make that journey from "Are you kidding?" to "Gee, maybe," and have you thought about the following problems, like cull regs, like being able to navigate, to today being our full-fledged partner, working with ONR today. They've been working with us to check out Sea Hunter, which we christened last spring, check out what it can do, and start working on demonstrating and experimenting with the kinds of new missions that this kind of a craft will enable. And I think we're now at a point where we have a Navy that is leaning forward and is very excited about, for example, having a vessel like this that without putting any human beings in harm's way could clear mines, or for a fraction of the cost of today's techniques could trail after a quiet submarine across thousands of nautical miles. These are radically new capabilities, and it's very exciting to see them start to become real. TURN is a program that's earlier in its life cycle. Here we ask the question, what if you could launch and recover a Predator-class UAV from the deck of a ship as small as a destroyer? Radical change in what a destroyer would be able to do if it had the ability to continuously launch, say, a pair of these that could leave, go many hundreds of nautical miles, provide ISR and even strike capability across that vast footprint. Very, very different than what a destroyer can do today. Here's a concept video so you get a sense of how completely radically crazy this aircraft could be. Leaving from a deck, imagine that in high sea states, and imagine coming home. And it transitions and off it goes. So we're at the beginning, we're at an earlier stage in this program, but I think this is another example of a completely different kind of capability that starts opening what's possible. So those are very interesting components, but let's talk a little bit about what starts becoming possible when you put all of these pieces together. Imagine a destroyer being able to launch, for example, that kind of a turn system with very sophisticated ISR capabilities that could find and identify, provide a target ID for an adversary craft in a time of conflict. When that information is relayed back to the destroyer, it could be provided perhaps through a comms link supported by an active type vessel, to an underwater asset, a submarine, which with a long-range torpedo could then execute a very successful strike against that adversary ship. So, and our CD MAST program is working on the cross-domain solutions that it's going to take to knit all of those systems together. The platforms, which make beautiful slides, are only part of the story, because think about the complexity of all those mission systems, what they have to do and how they have to work together. When that starts happening, you can imagine these kinds of much more capable systems of systems. And now think about this being done not over a few square nautical miles or even a few tens of nautical miles. Think about this being done over hundreds of nautical miles, and you start to see how powerful these architectures can be as we work to exert influence over the vast tracts of the open ocean. Okay, so those are some ideas about what's happening with weapons in the air and the maritime environment. Let's talk about the very human business of conflict on the ground. We have a whole host of programs in this area, and we are building beyond some of the work that happened just in the last few years that's rooted in the work we did in theater in recent years. A great example of that is the work in PCAS, for example, that brought the revolution in consumer electronics into the hands of our warfighters and gave them far better shared situational awareness. That work is playing out today when you watch the videos of Iraqis fighting in Mosul, supported by the U.S. Troops in a remote advise and assist mission. You will see them using those kinds of consumer devices to locate where artillery has landed. That's a direct descendant of the work that we've been doing here at DARPA. Looking forward, a lot of our focus has been on this issue of how do we empower small teams, squads and small units to control contested territory. And Squad X is an example of a program that's been developing a whole series of individual component technologies to expand the capabilities of a squad. And a critical part of this program, I think, has been getting on the ground and starting to do experiments with squads and trying to, and now really sorting out what's just going to be another gadget and what's really going to give you a major advance in combat capability. Here's a small video from a project where they worked. This is a field test that was done at Joint Base Cape Cod, and what they're working with is that drone that you see. It's got a camera on it. Drones and cameras, that's not new, but when you give that drone and camera the kind of intelligence that allows it to, for example, look over into a compound like this and be able to not only identify the individuals that it sees, figure out whether they're armed or not armed, track them as they move along, and do very similar things with vehicles. You start to see how these technologies can be not just another gadget for our soldiers to use, but can give them a level of situational awareness that dramatically enhances their capabilities. So I think we're on a very good path with this work. Okay, so conflict happens on the ground, in the maritime environment, in the air, but a whole series of things have to happen for us to be able to execute those fights. And one of them is what happens on orbit. We are critically reliant on space for every aspect of warfighting, whether it's position, navigation, and timing from GPS or communications or ISR. And we've had a marvelous run of it. The United States has gotten to own the space domain for many, many decades, but that world has gone. And today, with huge numbers of commercial assets on orbit, and now many more nations getting in on the act, it's a very complicated time on orbit. But DARPA is working on a series of programs that will allow us to achieve a future, we believe, where we can have robust operations in space again and be able to operate in a real-time fashion on orbit. Many pieces of this portfolio, one of the things we're working on is collapsing the amount of time that it takes to get a payload on orbit by changing launch. We're working on amazing new capabilities, for example, through our robotic servicer program to put a robotic servicer on GEO. But foundational to everything in space is to have a real-time, full understanding of what's happening on orbit. And today, we really just don't have that. Today, we live in a world of orbital catalog maintenance and forensic analysis of what might have happened on orbit. DARPA, again, is making great strides in moving us into the right future here. For example, we just have been able this last year to transition our space surveillance telescope to the Air Force. That allows us to look at dim objects on orbit across a wide swath of the sky continuously, a very big advance. Another program that I'll show you here is Orbit Outlook. And what Orbit Outlook has done over the last couple of years is develop the technologies to fuse data sources from observations, not just from government sensors that we know that we control, we understand what we're getting from them, but we're now able to fuse into our database data from university telescopes or commercial systems or data that comes from international partners. And that data now is getting fused in real time through Orbit Outlook with a quality stamp, so you know what you've got. But with hundreds of new sources, as you can imagine, we've dramatically expanded our Space Operations Center's ability to understand what's happening on orbit and to get to a real-time level of space domain awareness. Very important progress here. And the work here is transitioning to JIXBOC, and we believe ultimately to JSPOC, which I think is exactly where it needs to be to get that impact turned operational. That's space. I mentioned one of the things that we worry about a lot is something that we are critically reliant on orbit, and that is GPS. We all know it can be jammed on the ground. We know that our satellites could be vulnerable in a time of conflict. GPS, to me, is a great example of something that DARPA played a role in, especially in miniaturizing GPS receivers. In a sense, we were so successful that we've gotten the military completely addicted to this one technology, and now it becomes a critical point of failure in a time of conflict. So in a sense now, we're moving back to the future through a series of programs in a couple of different offices that take us from this critical reliance on GPS that we tap into all the time into a future where we have IMUs that don't drift as much, clocks that are far more stable, where we have alternative techniques for fix, not just GPS, but other signal sources of many different types, and the ability to very rapidly and seamlessly integrate all of those inputs. And so today in MTO, we are working on IMUs that will take IMUs of the quality that we have on satellites and shrink them down so that they could fit on a small diameter bomb. And in STOW, we recently did a demonstration on a Navy ship where we were able to repurpose signals that were being gathered already for SIGINT, but we've now been able to use those signals and fuse them into the PNT system on board to provide GPS quality fix. And so you start to see the pieces come together here that would allow us to have robust operations whether or not GPS is available. This next area is one that, as you can see, has a huge number of programs across the agency. We talk about all these radical new architectures. They're going to be very dependent on advances in ISR and in controlling the RF spectrum. I showed you a picture with lightning bolts connecting platforms. Every time you show one of those to a warfighter, what they're thinking is, how do I know that's actually going to work? And we live today in an RF environment in which, in fact, it's a very complex, tough job to have communications closed, to be able to jam an adversary when we need to be able to do our radar functions that we need, because technology has made it very easy for adversaries with software-defined radios, for example, to move very, very quickly. And so the course that we're on with this very wide set of programs at DARPA is to regain and actually to leap ahead with dynamic control of the spectrum across every wavelength that you could possibly imagine. One dimension of it is to collapse these massive systems that we use today through a program in MTO called ACT. This is the kind of result that it's getting. By digitizing and building A to D converters that have phenomenal bandwidth and sample rate, you can start to do the functions that today live in big boxes in these small modules. And these aren't just simple, sort of dumbed down RF modules. These are modules that have the flexibility to do all kinds of functions. And these kinds of advances in the ACT program now allow us to understand how we could start putting sophisticated RF capabilities with great robustness onto our distributed platforms that we see in the flexible architectures that we're trying to build. Today, when you want to build a new RF system, It's a $100 million undertaking to develop it for a new application of this sophistication. That could be $5 million with the kinds of advances that are coming out of ACT today. And then meanwhile, over in Stowe, they're working on RF systems that are going to provide some dramatic advances in capability. In a test this summer, Stowe was able to demonstrate in the CLASS program an 18 dB beamforming gain by having 3 transmit apertures received by 8 receiver apertures. Now, what does 18 dB mean to the warfighter? What it means is that when you're on the ground trying to transmit to your base station, instead of transmitting a watt, which lights you up like a beacon for the adversary to find, instead of one transmitter at a watt, 3 of those soldiers could be transmitting just 10 or 15 milliwatts that would be clearly received by our base station, but would be essentially impossible for an adversary to find. These are the kinds of massive advances that are starting to be possible at the RF systems level. And again, I think these are just 2 parts of many things that we're doing that are going to give us this dominant position in the electromagnetic spectrum. Okay, so a lot of what we've been talking about depends on building electronics and building it in a way that we can trust. The way we have solved this problem in recent years in the Defense Department has been to say we're going to build a walled garden, and we're going to make sure that every design for a custom integrated circuit that we build is completely protected. No, it won't leave shore. It'll only be handled with people who are cleared to handle it. And that's how we'll know that our custom integrated circuits that what we're designing can't be revealed to an adversary and that it can't be tampered with by an adversary. Sounds like a good idea, but what has happened over a period of time is that we've built a little island for ourselves in which we move much more slowly than commercial industry, and we are many process nodes behind. So we're not getting the full benefit of that explosion in capability that continues as a $300 billion a year commercial semiconductor industry drives integrated circuit technology forward. So in MTO, they've developed a marvelous portfolio of programs that are going to ultimately, collectively, these programs will allow us to tap the leading edge of commercial global silicon technology, but do it in a way that builds in trust so that we know our designs haven't been revealed and that they haven't been tampered with. I just want to show you one example of what we're doing in this area. It just tickles my funny bone as a former microelectronics person myself. Back in 1958, a couple of things happened. DARPA got formed. The integrated circuit got invented. And the key insight of the integrated circuit, for those of you who don't live in this world, was the idea that at that time, all these individual transistors that people were building worked fine, but then the interconnects were just this rat's nest, and it was impossible to build big systems. The key insight of the integrated circuit revolution was the idea that you could build those interconnects, you could build those wires on the same substrate, the same semiconductor material as the transistors. It started with just a few transistors. Today, if you crack open your smartphone, you'll find chips inside that have tens of billions of transistors. So Moore's Law has really gone a long way across many, many decades, nearly 6 decades today. Now, the problem is that those multi-tens of billions of transistors on an integrated circuit and all those interconnects have become so hard, so costly, so slow to design that only a very few companies around the world build product of that complexity. And none of those companies are defense contractors. Again, DoD has not been able to operate at that leading edge. The CHIPS program at DARPA stands Moore's Law on its head with the insight that if we can build chiplets that embody the intellectual property for specific kinds of circuits, that those chiplets now can be assembled on an interposer with dense interconnect in a way that would allow us to completely change the way we design very huge, complex electronic circuits. And it's one part of what MTO is doing to make these advances in microelectronics something that we can harness for defense systems. And it tickles my funny bone because who besides DARPA would blow up Moore's Law? I mean, only us. We're the only ones. Okay, so we have been walking from the world, the physical world, to the information world. Let's just plunge right in. One of DARPA's huge ambitions today is to win at cyber. easy to say, but when you say this to people who live in the cyber conflict, in the world of cyber conflict, they look at you like you're crazy, because of course every day when you open the paper, what it feels like is that we are losing at cyber. We are more and more reliant on complex information systems, more and more reliant on data, and yet we have less and less confidence in those systems, it seems, with each passing year. The portfolio that I2O has been pursuing in cyber is putting together the technology elements that would allow us to reverse that and to be able to win at cyber. In some cases by taking whole classes of vulnerabilities off the table, in some cases by learning how to operate through cyber attack, and with other tools learning how to engage in cyber operations and cyber conflict in a way that would allow us to prevail. Many, many big stories in this portfolio, but let me just share one with you, and it's work that comes out of the Cyber Grand Challenge. The tools that have been developed through the Cyber Grand Challenge are going to have many different implications. So let me just walk you through one. Today, when we deploy software, that might be a new browser that gets deployed, or a new operating system, or new application. It might be one of our DoD systems. As soon as that software is deployed, adversaries go to work looking for flaws in that code. And over a period of many weeks, sometimes months or even years, when they find flaws, they build attacks. And when they decide, they activate those attacks. And when those attacks happen is often the first signal we have that we have that particular flaw. And so then our side goes to work and we try to find that flaw that's being exploited, build our defenses. But of course, meanwhile, the adversary has succeeded with that attack and perhaps is proliferating it throughout our systems. With the Cyber Grand Challenge, what that competition did was challenge teams to build computer systems that could do the kind of human reasoning that I just outlined for you that people do today by crawling over code. Very expert cybersecurity professionals and hackers who look at code and try to find these flaws and build defenses. CGC said, can machines do that? And in fact, what we found was that machines could do much of that at a speed that is so significantly different that you actually now have to move to a different time scale. So that attack, which seemed like a moment in time, because we're thinking in time scales of months, is actually something that happens over a period of minutes or maybe hours. And Cyber Grand Challenge technologies can show us that there's a future where when an attack begins, a machine could actually discover the same flaw, build its defenses, and implement those defenses before the attack is able to succeed and proliferate. A complete game changer, a radical advance in our ability to deal with cybersecurity threats. Just one example, but I think a powerful one. So, great, if we achieve a future where we believe in our information systems and believe in our data, what is all of that data for? We're living in a period in which we are awash in this primordial soup of ones and zeros. And in this environment, we are also finding amazing tools, data analytics tools, artificial intelligence tools that allow us to solve an unimaginably wide variety of problems that have been intractable to date. And in the portfolio across DARPA, multiple offices, you'll see work that we're doing to harness data, to synthesize chemicals in completely new ways, design complex systems in new ways, advance our ability to deal with natural language. But these examples, just to cite a few, some of these examples actually lie in some of the areas we've already talked about. So if you look inside of our sophisticated new military systems, you find artificial intelligence, for example, that's part of how Sea Hunter navigates. In the area of Spectrum that I talked about, one of our big new programs in MTO is the Spectrum Collaboration Challenge. This is a competition that will challenge teams to build radio networks with embedded AI that will scan the radio spectrum and form hypotheses about how others are transmitting data in order to optimize how it transmits its own data. It's going to be a crazy competition because not only will teams get points for successfully transmitting their data, they get half points if the other teams are also successful, because what we're aiming to do is to develop the techniques that allow us to get multiple times as much wireless data through a fixed amount of spectrum. We're already in a period where DoD needs and commercial needs for spectrum are colliding. As our needs grow and as the Internet of Things explodes, you can imagine that that's only going to get worse. But through these kinds of techniques in the Spectrum Collaboration Challenge, again, thinking about data in the radio spectrum and finding these very powerful tools to harness that data, you can start to see how we might make the advances that allow that future to unfold. We're using data in many, many different ways in cybersecurity. A very different example than Cyber Grand Challenge is our network defense program that looks at many, many tens or hundreds of billions of network transactions in a network, and within that vast set of data is able, through very sophisticated math and data analysis, to find tiny anomalies, just a handful of transactions that might be the beginning of a problem that a security professional needs to track down. And of course, we're using these techniques of data analytics and AI in the online environment. In our MEMEX program, we built tools that law enforcement is now using to search not just the surface web, but the deep web and the dark web to find networks of human trafficking. They're using those tools today already in hundreds of investigations, in 27 indictments, and to date, 3 convictions. I hope there's a lot more ahead. And as we do this work, you start to see the kinds of tools that are going to be critical for the kinds of conflicts that are happening in the information domain. That's becoming an integral part of conflict, whether it's with Russia or against ISIL. These are the kinds of things that are part of the future of national security, and these are the kinds of tools that are going to be critical to give us eyes to see what's going on in that environment. So huge numbers of applications because of the power of the tools that we currently have in data analytics and artificial intelligence. But when we look at those tools and capabilities, as we're doing this work, we are also very aware of what some of the quite fundamental limitations are today. And so part of our work at DARPA, and one of our big ambitions at DARPA, is to build the tools that allow us to go dramatically farther than what we have today in understanding and then using complexity. And again, a whole raft of different components in what we're doing here, tools that help us move from simply understanding correlation to being able to map causal relationships, tools that will change how humans and machines team up to solve complex problems. But let me start by giving you one example that is part of the problem that we struggle with artificial intelligence. I think people have seen, you came to our wonderful fomenting talk on artificial intelligence. You know that statistical learning systems today have gotten very, very powerful. Every week you read about one that's statistically better than human performance. One example is systems that label images. Here's an example of a machine that identified what was going on in this image, and they're very, very, very good, sometimes statistically better than humans in many cases. But that doesn't mean they're perfect, and when they make mistakes, they make the kinds of mistakes that no human would ever make. And this has incredibly important implications for how we use and where we trust statistical learning systems in AI today. For example, if you're going to look at signals in the radio spectrum, this is still a great technique because once in a while if you have a problem, it really just doesn't matter. On the other hand, if you're making critical decisions for your self-driving car, or in our world for a targeting decision, these technologies are not ready for prime time. And at DARPA, when we see that, we try to be very clear with the users of our technologies about their limitations, but then we go to work and try to move beyond today's limitations. And that's the objective, for example, of the Explainable AI program in I2O. Today, these statistical learning systems train on vast amounts of data. All their nodes get trained in their deep neural networks. But when they come up with a confusing result and you open the lid and you look inside, what you find is a bunch of node weights. You have no way of understanding how it arrived at that decision from the millions of images that it was trained on. The Explainable AI program aims to create AI technologies that keep that high performance level, but that build in the ability to explain how these machines arrived at these conclusions. For those of you who follow this field, you know it seems sometimes to be all about identifying cats, so I guess that's why we have a cat image. But here's an example where now you might look inside this black box and the system could tell you why it identified that particular image as a cat. This is going to be essential for us to be able to know why our systems do what they do, and then to know when to trust them and how to continue to improve them. That's an important advance. Here's a very different example of an area where tools are now starting to become available that we think are going to give us the ability to push the frontier of tractable problems in the social sciences. Today, when we want to understand questions, for example, this sample question of the key factors in the formation of a collective identity, the kind of research that we do today is sort of limited. You recruit a bunch of graduate students, you run some experiments, and then you try to generalize from that, and lo and behold, it doesn't tell you much about what's happening in stressed communities in other parts of the world. Today, though, we have a whole range of new tools. One of them is the online environment in which games and experiments allow us to do a kind of experimentation of a different scale and with a much wider reach. And one of our new programs, the Next Generation Social Science Program in DSO, aims to develop the tools and methods that allow us to tackle social science problems in ways that are replicable and reproducible and extensible in a meaningful way to the problems around the world. And the sample problem that program is working on is exactly this question of the key factors in the formation of a collective identity. And I think, to me, it's a great reminder that the key questions about human behavior, societal behavior, it's hard to think of anything that is more fundamental to the business of national security. And if there are, in fact, new techniques that would allow us to move the frontier of understanding forward, I think this is an incredibly high return area for DARPA to be pursuing. Okay, I'm going to finish with a couple of examples from biology. When I talked about the places where we look for new technological revolutions to happen, biology today is one of those places where things are happening. You go to conferences and you see biology colliding with physical sciences and engineering with information technology, and the advances that are happening are breathtaking. They are going to be used for all kinds of wonderful advances, and they are also going to be very, very dangerous. And when we see that kind of technological bubbling and brewing, this is a place that DARPA wants to pile into to drive new technological capability and to do it in a way that we think will lead to the greatest opportunity for positive applications while mitigating the downside risks. One of those areas within biology today is what's happening with synthetic biology and genetic engineering. This is an area where DARPA has a collection of programs in BTO. For example, engineering microbial communities in ways that are safe and controllable. One new example that I want to walk you through is our Safe Genes program. And this program was created because every time you open a scientific journal, it seems, in the last year or two, what you learn about is this huge advance with CRISPR-Cas9, a gene editing technique that is so much more precise and capable than what biologists have had, that it has swept the research community. And it seems like overnight everyone's using CRISPR-Cas9 to do some kind of genetic engineering. Now, there are huge applications ahead. This is a concept that I'll walk you through. There's no DARPA logo on this slide because this is not a DARPA concept, but I want to use it as an example of the kinds of very powerful capabilities that people are thinking about. This particular application is about dealing with the problems of malaria. Malaria is a disease that hundreds of millions of people suffer from around the world, and in a given year, many hundreds of thousands of people die from malaria. And to date, we've made some progress, but we really haven't found cost-effective ways to completely drive that problem to closure. Gene drives are a concept that is catching fire today because of the following possibility. Here's the concept. It starts by engineering a mosquito's genome to do two things. One is to engineer in a trait that would reduce its ability or stop its ability to spread malaria. And the second is a gene drive. What that gene drive does is that when that engineered mosquito is released into the wild, as it mates with wild type mosquitoes, let's see if I can get back to the right slide, as it mates with wild type mosquitoes, those offspring, it's not just half of them that have the engineered trait that you want, but virtually all of them, because the gene drive that's what gene drives do, is they drive it through the population that rapidly. That's why people think that this could ultimately be finally a cheap way to start getting at malaria's problems. Now, usually when people start a conversation about species-level genetic engineering, usually the reaction is that really moral? Is that really ethical? Today, people are making the argument that with the number of lives at stake because of malaria, if we could do this, it might be unethical not to do it. So really a very, very interesting time. Now, I'll note that this is actually not yet quite technically possible, but it seems like a pretty good time for DARPA to think about the kinds of technologies that would allow us to do these kinds of things, but with the kind of control that's critically important here. And so the Safe Genes program has 3 components. One is to continue to develop better gene editors that are more controllable and reversible on the left-hand side of this picture. On the right-hand side, to develop techniques that would inhibit the effectiveness of a gene edit in an ecosystem, whether that's something that's the consequence of bioerror, an off-target effect, or bioterror. We want to be able to inhibit those effects. And the third leg of that program is to find techniques to reverse a community back to baseline after an ecosystem has been subject to gene editing. Very ambitious goals, but I think a great example of how DARPA can chart a course in this fast-moving arena. This is my second example from biology, and it's the work that we've been doing in neurotechnology through a collection of programs, again in BTO. I think most people at DARPA know that this work began with the Revolutionizing Prosthetics program, in which DARPA set out to restore natural function for our wounded warriors. Upper limb prosthetics really had been stuck with the very simple hook as the standard of care. We set out to build something that would give a wounded warrior a completely different level of capability. This image that you see here is not an artist's concept. This is a photograph of a product that has come out of this program, and it is a mechanical arm and hand that is about the weight of a human arm, an adult human arm, and has the degrees of freedom that really allow for a completely different level of capability. A huge advance, one I'm very proud that we've developed and gotten through FDA and is now commercially available. This device is controlled by twitching a toe or flexing a muscle, and DARPA, of course, was reaching for something much more when we started the Revolutionizing Prosthetics program. We wanted to have not only the mechanical arm with all of its capabilities, but near natural control of that arm. And so the other branch of this program was to develop the ability to directly sense and to interpret in real time the very precise neural signals from the motor cortex and to the sensory cortex, and see if we could start using those to give people an ability to sense what's happening with their arm, with their mechanical arm, and to be able to control it. And I want to show you a quick video with 4 of the volunteers over the course of the last several years who've been part of the RP program, and you'll see the first 2 being able to control their mechanical arms with just their thoughts, and then the last 2 you'll see the sensory side of it.
Baby, I want to hold your hand. Baby.
I can move it up and straight down and left and right and diagonally, and I can do a fist bump if you'd like.
That's amazing.
Middle, index and middle.
Oh my God, I just felt that roar. God, that is so cool.
That last one is Doug, who's been an amputee for a couple of decades, having lost his forearms in an industrial accident. And as he moves his residual limb, he's able to control that virtual hand. When it touches the virtual door for the first time in a couple of decades, he's now able to get a sensory perception that is, to his brain, it is exactly what he would have felt, what he had been able to feel when he still had his natural hand. So I think, and especially when you think about that virtual environment, I think you start to see not just the things that we can do to restore function, hugely meaningful, but out beyond that, you can see that the window has opened to all dimensions of enhancing function. And the work that we're doing on motor control and sensory perception is only part of the neurotech portfolio, very wide set of activities. Taken together, this work, I think, starts to show you what we're now beginning to imagine about how human-machine symbiosis might develop even beyond what we in our powerful machines do through a screen. So I have now shared with you a dozen big ambitions across the portfolio here at DARPA, and 12 is a really good number. It's a nice round number. I like 13. And I think it's because after you work on the 13th floor for a while, you start thinking 13 is a good number. It's a prime number. So I want to finish my list of big ambitions with the one that I think is the most important. Because DARPA is not a place where there's a roadmap or a list of things that you need to go work on. Every single big ambition that I've just shown you came out of program managers' ideas and your programs and your seedlings. And it is vitally important that we keep that going. And when I look at the work that's going on outside of these big ambitions that we're driving, this is why I know DARPA is also doing the work to keep moving forward and move into the future. Okay, so all of that is a tour through the work that DARPA is doing here in the mid-teen years of the 21st century. And not everything I showed you is going to work. When you take these kinds of technical risks, not everything succeeds. But in this portfolio are the technologies that are going to fundamentally recast military capabilities and change national security outcomes. And in this portfolio are the technologies that are going to fundamentally change how we live and work in societies around the world. Now, next month, DARPA will be at a new threshold. And when I leave in January, I have the rare and truly wonderful situation of leaving with full confidence in what I leave behind. And the biggest reason for that is Steve Walker. Steve and I have worked in close partnership together for 4 years now. And Steve, I know you really well. I've seen you through a lot of things. And I know you are DARPA to the core. And I know that you and Stephanie Tompkins and the whole team here are going to chart a terrific course going forward. So I want to end my remarks today by simply saying to all of you, please know that I will be watching in pride as you build the future. Thank you very much.